Hello. In the last few lectures, we have been discussing about multi-step methods. So, we started with explicit methods, then implicit, and then we discussed some stability aspects, and then how a combination of explicit implicit methods can be used as predictor corrector methods to improve upon the solution. Okay. So, we have given some motivation for the multi-step methods, okay. But however, I would like to mention here a different motivation and then some comments on multi-step methods. Okay. So, it is a kind of alternative approach, but it is a intuitive. Okay. So, let us start with that. So, alternate ideas behind corrector. Okay. So, suppose this is our y I plus 1 and this is the approximation. Okay. Let us denote some other notation. So, then this is matches slope for this. Okay. So, this can be thought of as first approximation. Okay. Suppose this matches slope and curvature. Okay. So, then this can be thought as second order approximation. Okay. So, if y dash of x I is slope, okay, is known, then it is a first order approximation. If slope and curvature are known, second order approximation. Okay. But the fact is curvature is proportional to y double prime. Okay. So, hence the question is, can we find approximation to y I double using already computed values. Okay. So, this is the motivation. Okay. Can we approximate this person? Okay. So, usual approximations y I double minus by h, usual difference approximation, okay. Then y I plus 1 is So, Taylor series so y I double prime, can we approximate this using past point? So, here is the answer. So, we substitute so this is okay. So, we got a kind of multi-step method. Okay. So, what did we do? Just this is a Taylor series expansion, but then the second derivatives have been approximated by the corresponding finite differences which involve past points. Okay. But star becomes exact rather than approximate if y of x is polynomial degree 2. Okay. Cos y I prime is 2 x I plus b, then y I double is 2 a by h. Okay. So, this star becomes exact rather than approximation if, because the coefficients are determined. Okay. Okay. So, star is second order. Okay. However, if one needs third order, what would we do? Okay, let us consider this. So, again finite difference approximation. Then we get so this is our new star. Okay. But the question is, see, in the earlier case we have substituted, in the earlier case we have substituted for y I double only up to order of h. Okay. But now we would like to go for higher. So, in order to use y I double, which is up to order of h in star, we need an expression for this, because we have to increase, right, an expression. See, this is h square. So, you need third order. So, you need an expression for this, so that h square times this you get third order. Okay. So, an expression for the order h term. Okay. with accuracy h square. Okay. So, how do we do it? Y I prime minus okay. For the second derivative, we want to increase the order. So, therefore, so now if we substitute this, star would lead to which is Adams-Bashforth third order method. Okay. So, this is a kind of alternative thought. Okay. I mean, this is a little unusual, but this is a kind of alternative thought. Okay. So, this gives the multi-step method. So, one can derive other methods. Okay. So, now if you recall in the one of the earlier lectures, so given see a general linear multi-step method can be expressed in terms of two characteristic polynomials, that is the first characteristic and the second. So, now one of the question that was posed was, given the first one, can we determine the second characteristic polynomial, so that the corresponding multi-step method is determined. So, that was a bit unfinished. So, let us try to recall this and then try to compute for a particular case. Okay. So, given to compute, okay. So, we consider our multi-step method. I would like to make a remark. So, this can be written in different notations. So, I do not want you to remember, we should be able to write within any general notation. Okay. So, sometimes like this, sometimes with n plus j combination. Okay. So, this is our multi-step method, then the corresponding error Okay. Now, the linear multi-step method set to be of order p equal to 0 and C p plus 1 non-zero. Okay. So, accordingly T I plus 1 we get this, that is identically 0 when y x is a polynomial of degree less than or equal to p. Okay. Yeah. Now, observe that C I and p order of the method, okay, are independent of y of x. Okay. So, choose y of x as e power x, accordingly this, then your double star, which is the error, this becomes okay. So, this is e power if I take e power x I minus k plus 1 common, e power k h e power h minus x okay. This so, using this notation, this can be written as rho of h sigma of because this is the characteristic, first characteristic and second. Okay. So, but then this must be equals to okay. So, From these two we can so by some terms of this will be left, that is e power 1 minus k. So, that e power k minus 1 so this is h times 1 minus k. So, that is given to this coefficient. So, with adjustment it can be written like this. Okay. So, now this becomes the basis for finding, given this, how to find the second characteristic polynomial. How do we do it? Let us proceed. Set this as h goes to 0 1, then log zeta, we write it as zeta minus 1 plus 1, and we write it an expansion. Okay. Further, h power p plus 1 is log zeta Okay. So, now these two we use it here. So, therefore, okay, if is given the above can be used to find rho. Okay. How do we do it? Expand in, then retain terms of required order. Okay. So, another remark is implicit or of same order, rather degree, explicit rho is 1 higher. Okay. So, let us work it out with an example. Okay. So, given find this. Okay. So, looking at this, so this implies so degree of 1. Okay. For of course, for a explicit method. So, this is Okay. So, now this is okay. So, this can be further simplified as so what we have taken? We have cancelled out zeta minus 1. So, we have expanded. So, therefore, this equals to because of the second degree we have expanded up to that and we have got sigma. So, therefore, the method is so this is a method explicit which is of second order. Okay. So, what did we do? Given this, we have expanded so this is h is a log zeta. So, I have divided. So, this rho by rho by log zeta we have expanded. Okay. So, rho by log zeta we have expanded. Okay. So, then up to second order. So, that should be of order sigma, okay. Neglecting of second order, that should be sigma, and hence the method is given by this. Okay. So, this gives a sense of computing first characteristic polynomial, second characteristic polynomial, vice versa. Okay. So, now, so there is another aspect related to multi-step methods which I would like to mention. Stiff systems. Okay. So, consider, so stiff systems has to do with the system of equations, but however, while solving using multi-step methods, it is important to study stiff systems, okay, in the context of multi-step methods. So, we have a system. So, example, say A is okay, with conditions where x bar is say x 1 of t and x 1 of 0. So, this implies x 1 of t is okay. So, we have an equation like this system, the coefficient matrix is like this, with these initial conditions we get the solution. So, this becomes this is after a short time. The reason is you have a big coefficient multiplying t. So, after short time this decays faster than this. So, after short time we have this solution. Okay. Right. So, what is great about this system? It is a very fudgy kind of a term, stiffness, solution of interest. What are they? We expect solutions of interest means they are of the form e power lambda t kind of solutions, right, or slowly varying but solutions with rapidly changing structure are possible. So, look at this. So, these are the solutions of interest, but however, you have solutions that are rapidly changing. Okay. So, let us define more precisely. So, a system is called stiff if a numerical method with a finite region of absolute stability applied to a system with any initial conditions is forced to use in a certain interval of integration a step size which is excessively small in relation to the smoothness of the exact solution in that interval. So, what it says, a system is called stiff if a numerical method with a finite region of absolute stability applied to a system with any initial conditions is forced to use in a certain interval of integration a step size which is excessively small. That means, your exact solution is really smooth up to some order, but however, the step size that the method is demanding is not in correlation. Okay. So, we can analyze this a little more carefully. Okay. So, let us analyze with respect to system. Consider system that means system of IVPs okay. So, where so, these are the unknowns. So, example so, here our y was okay, and okay. This is an example. So, now we have learnt how to solve an IVP for a single component. Okay. But then suppose if we extend a similar method to this, we must arrive at a multi-step method. Okay. So, a linear k-step method for the numerical solution of 1 we expect to have the following form. Okay. Okay. So, now let us assume that this f vector is of this form. So, for example, f bar is x plus y 1 minus y 2. So, this we need to express okay. So, this is possible, this is possible. So, we need to get y 1 minus y 2 and 0 plus. So, this is our A and this is okay. Suppose we are assuming like this. So, constant matrix and B bar column. Okay, this is a column matrix. Then your multi-step method gets reduced to where okay. So, this is a simple exercise with reference to this split up. If you put it in your multi-step method, we can check the multi-step method reduces to this. Okay. Let the eigenvalues of matrix A are distinct, their lambda I. Okay. Then there exists a non-singular matrix H such that can you guess what would be the matrix? Yes, of course, the eigenvalue entries, the diagonal matrix with the eigenvalues. Okay. Then define. So, what for we are doing? See, look at this. We know how to solve a single in multi-step method for a single component. So, you have initial value problem. Let us say this is a single component. We have a multi-step method. Then we know how to analyze, how to compute the solution and how to analyze whether the method is stable or not. But then for a system, it is coupled. You can see. So, unless you arrive at a corresponding multi-step method which is decoupled we are not in a position to comment on the stability and overall behavior of the system. So, we are trying to do that. Okay. So, define this, and C is, so then we get so this is say m star. Okay. So, then m star becomes A j. So, your m star contain identity matrix. So, this one can write H inverse H. So, I would like to write minus H b j, and A is okay. Okay. So, it can be written like this. Or the same thing can be written as this is the component, ith component of the vector. Okay. So, this is, you can see this is a corresponding eigenvalue and this is the corresponding component of the vector z, and what was our definition. Okay. So, what did we achieve? Each equation for a particular value of I is decoupled and is similar to a linear multi-step method. Okay. But only one remark, h bar equals lambda h can be complex. Okay. Right. So, now one can discuss the stability of each one can discuss the stability, because now each equation is like a linear multi-step method, but only thing is this is complex. So, within the context of this complex, let us discuss the absolute stability region. So, a linear k step method is said to be absolutely stable in a set R A of the complex plane if for all h bar in this all roots R s 1 to k of the stability polynomial satisfy this, then the set R A is called region of absolute stability. Okay. So, let us see for a single component case. So, for example, so we have this and we have okay. So, pi is so this equals to 0, this implies z equals to so we need the region so this implies so this is the region okay right. Suppose consider Euler method. Then pi is given by okay. So, this implies R is 1 plus h bar and the region R A will be h bar belongs to the complex plane such that so what is this? So, this is a open circle centered at -1. So, this is the stability region. Okay. So, for a system also one can discuss okay. And one can observe that for a system if the stability region is dictating some range, however, the solution is demanding very smaller h okay, due to the extraneous terms. Okay. So, then really the system is stiff in that context. Okay. So, this gives some idea on the stiff system. Okay. So, you can refer the notes by Zuli for better understanding with respect to examples. Okay. So, more or less this gives some idea of multi-step methods, predictor corrector methods, etc. Okay. Thank you. Bye.